Hi, my name is Wenmin Chen. I am going to present WASAI, a concrete fuzzer to detect vulnerabilities in WebAssembly smart contracts. The concrete fuzzer uses symbolic execution to build past constraints, and then solve them to generate effective Cs that can touch the deep code of the smart contracts. WebAssembly is a new instruction set. We also call it Wasm. It is open, high performance, and safe. WebAssembly is widely used in blockchain to implement smart contracts. Smart contract is a cloud executable that can access blockchain. EOSIO is the first Wasm blockchain launched in 2018. Following EOSIO, there are several projects also choose Wasm as their development stack, including Polkadot, Neo, and Solana. Wasm blockchain is a hot topic. We focus on EOSIO because it is one of the most popular and fastest Wasm blockchain. The highest market capability is near the 18 million US dollar in April 2018. Nowadays, there are over 5.2 million accounts in EOSIO. We believe that the analysis of EOSIO can apply to other Wasm blockchain. My presentation starts from the vulnerabilities in EOSIO. After that, I will show the limitation of the existing tools. To surpass them, we design WASAI. In the third step, at last, I will show the evaluation results. The official team of EOSIO creates a smart contract named EOS token to issue one kind of cryptocurrency, EOS. Transferring EOS means updating the balance records in EOS tokens database. I use the example showing this picture to explain the transaction mechanism. The player can pay the EOS to the lottery smart contract named EOS bet for the jackpot. To this end, he has to interact with EOS token rather than the EOS bet. In the step 1, the player calls the transfer function of EOS token. Next, EOS token callbacks the payers and send a notification message to the EOS bet. Last, EOS bet interact with EOS token to reward a lucky user. In EOSIO, smart contracts developers may miss some verification and cause serious consequences, like losing cryptocurrency. Following previous studies, we aim to detect 5 kinds of commonly seen vulnerabilities in EOSIO. In fake EOS, the victim may accidentally accept fake token if he doesn't check the token issuer, because any EOSIO smart contract can issue token using any name. Fake notification evolves from fake EOS. The attacker can forge a EOS notification to pretend to be EOS token if the victim doesn't verify the notification message. For mis-authority bug, the attacker can perform behaviors on behalf of others if the victim doesn't check the user authority. For block info dependency, the attacker may predict the random number used in smart contract if the victim used the blockchain information as random seed. As for rollback, the attacker can revert the execution to deny the transaction if the victim packed the bad behavior and the revolt behavior in the same transaction. To the best of our knowledge, only a handful of studies focus on Wasm smart contracts, which can be classified into 2 categories. The first one is symbolic execution-based static tools, such as EOSafe and WANA. If the target contract is too complex, they may fail to solve constraints and rise timeout due to the past exposure. Another category is dynamic fuzzing, such as EOS fuzzer. However, EOS fuzzer only generates random seeds and it doesn't identify the transaction dependency to analyze the smart contract. which is actually a stateful program. Here is the WASAI design. First, we instrument the target smart contract to obtain the execution trees. Next, we build symbolic variables for the input data. Third, we simulate traces to build constraints along the path. By solving them, we can generate new seeds to touch the unexposed branches. We also schedule the seeds. For example, we analyze the data dependency of the persistent data to construct transaction sequences with several seeds. We also use tempo-based payload of seeds to trigger the vulnerabilities. Alas, the scanner identifies the exposed events from the traces and outputs a report. We face three challenges. The first one is about how to acquire traces. The existing solution instrument Wasm interpreter, which supports multiple threads execution. It further sacrifice the efficiency to execute smart contracts one by one to avoid missing out the traces from different smart contracts. In our solution, we perform a contract-level instrumentation, which ingests low-level hooks to Wasm bytecode. The hooks execute along with the instruction of the smart contracts. The second challenge is about how to build a memory model. During concurrent fuzzing, memory instruction may use a symbolic expression as the address. For example, there are two nested store instruction highlighted in blue, which set the value in address A as 0 and then store FFFF with the address B. Only when A and B are equal, we can know the data from A to A plus 4 is FFFF rather than 0. To solve this, we build a memory model based on byte vectors. We also construct a symbolic load object for each load instruction that reads and saves memory data. The SMT solver will resolve the symbolic load objects by finding a certain address first, and then solves the remaining constraints. The third challenge is the calling convention before the target Wasm function is executed, which is we concerned. The smart contract has to deserialize the input data into meaningful objects. WASAI had to skip them to avoid path exposure. After skipped, we unfortunately maybe we lost the mapping from the set of function arguments, and consequently the seed mutation will be affected. Our solution recovered the mapping by inferring the specific arguments in the WASAI layout of each input data. So the three solutions are embedded in the WASAI components such as signback and scanner. In signback, we first construct the calling convention. This is a consistent one-to-one mapping between the runtime values and the C parameter in the context of action function. We find these rules based on our observation. The function parameters are initiated as local variables, which are defined explicitly in Wasm layout. The argument row I is the local variable Li. The below table shows how we infer the input for the transfer function used in US token, which include 4 parameters. The signback builds and shows symbolic constraints for further feedback. This table shows the operational semantic of each Wasm instruction, which guides signback to perform symbolic execution. At last, we define 5 oracles to scan the exposed events from the traces and then output a bug report. To mention the code coverage of WASAI, we randomly select 100 renewal smart contracts from the US blockchain. We run WASAI and use fast 5 minutes to analyze this benchmark. In the beginning, WASAI has to spend extra time on SMT solving, resulting slightly lower code coverage than EOS fuzzer. However, it surpasses the EOS fuzzer after 10 seconds. The result shows that WASAI achieved about twice as much code coverage than the baselines. In argue2, we create a dataset via injecting verified bugs into real-world contracts, just like Lava. For fake EOS and fake notification vulnerabilities, we remove the get code from the safe samples to generate vulnerable ones. For mis-authorities vulnerability, we remove and add permission APIs to generate grand truths. As for bulk info dependency and rollback vulnerabilities, we generate samples by customizing the source code. As a result, WASAI outperforms all state-of-the-art techniques on a large-scale benchmark with 100 of precision and 98.4% of records. In RQ3, we evaluate the robustness of WASAI with two benchmarks. We generate the first benchmark by obfuscating the sample in RQ2. The result demonstrates that WASAI can retain high accuracy, while the state 2 is safe is very sharply because it cannot find visible paths in bug detection. In the second benchmark, we inject complicated checks into the sample in RQ2. For example, we will assert one input data must be equal to some specific constant. We found that WASAI still retain high performance, while EOS fuzzer, another dynamic fuzzer, has poor performance because EOS fuzzer redundancy cannot touch the deep code of the smart contracts. As a result, WASAI is more robust than the baselines. In Q4, we apply WASAI to real-world smart contracts. We collect almost 1,000 smart contracts that can accept EOS token. And we found over 70% of them are flagged as vulnerable. 413 of them are still alive on the mainnet, but only 72 of them have been patched. Note that WASAI identified one zero-day vulnerability, which has been assigned with a CV identifier. As a result, we revolve the urgency of fixing the vulnerabilities in EOS smart contracts. In conclusion, we propose WASAI. The first concrete fuzzer for WASAI smart contracts, we construct a large-scale benchmark to evaluate WASAI. The result demonstrates that WASAI outperforms baselines in terms of code coverage, accuracy, and robustness. We also apply WASAI to real-world smart contracts. By the time of this study, over 300 of them had not been patched yet, which includes one CV vulnerabilities. That's all. Thank you.